Good morning, everybody. My name is Dr. L. Lakshmi Prasanna Kumar, Assistant Professor, Electronics and Communication Engineering Department, G. Pullareddy Engineering College, Autonomous Kurnool. Today we'll have the introduction of why we require the AC equivalent model, especially for designing the amplifier. In our daily life, we are starting the day with amplifiers and ending the day with amplifiers. In all communication systems, irrespective of wired and wireless communications, designing the amplifiers is playing a major role. Without amplifiers, we can't imagine any application. Not only that, even current scenario of communication, advanced communication system, 4G, 5G, and IoT devices, even if you want to drive the autonomous cars, if we want to drive the autonomous robots, we want to have the autonomous vehicles, definitely the communication is playing an important role. In that communication, amplifier is playing a major role. That's why we are initially concentrating that what are the parameters required for designing the amplifiers. Understanding the amplifiers a little bit complex and little bit tricky. That what are the internal structure of an amplifier and on what parameters these amplifiers are depending. For example, you consider this is an amplifier. I'm applying an input signal and I'm getting an amplified output. Getting an amplification output is a major task. In some cases, we are getting only the positive cycle is amplified and the negative cycle is not amplified. This is not amplification. Amplification means 0 to 360 degrees have to amplify. Then only we are calling as linear amplification. The aim of a communication engineer, we have to design a specified amplifier in order to achieve the linear amplification. In order to achieve the linear amplification, we require certain parameters to understand the designing of the amplifiers. And those parameters are known as voltage gain, current gain, input resistance, and output resistance. These are the four major parameters of the amplifier. Without knowledge of these four parameters, it's very difficult for us to design the amplifiers and on what parameter this amplifier is dependent. And even if you want to adjust the internal parameters of the amplifier also, we require the knowledge of voltage gain, current gain, input resistance, and output resistance. But it is not that much of easy. If you want to concentrate these parameters, we require the knowledge of H parameters. H parameters are nothing but the hybrid parameters that will explain the internal structure of the transistor. Transistor is a semiconductor device. Of course, transferring of resistance we can experience inside a transistor. And we used to transistor in a different configurations like CE, CB, and CC. These three configurations already we are coming across in lower standards in EDC. But just understanding the configurations, our task is not complete. Transistor is not equivalent to a, if transistor is not equivalent to an electrical device, it is not possible to understand the internal behavior of a transistor. Exteriorly, we are seeing the transistor as only emitter, base, and collector. But if you see the transistor only emitter, base, and collector as an electronic device, it is not possible to design the perfect amplifiers according to our expectations. That's why first we have to consider the transistor as a two-port network. Unless until if you are not considering transistor as a two-port network, unless until if you are not making the transistor is an equivalent to electrical component, it is not possible to know that how we have to find out the H parameters. Why? Because H parameters are very crucial in order to find out all the parameters of the amplifier. That is the reason first we have to consider the transistor is an equivalent to a two-port network. So in that process, the first condition what I am considering, transistor is a two-port network. Transistor is equivalent to a two-port network. If you are not considering transistor is equivalent to a two-port network, it's very difficult for us to find out the internal behavior of a transistor. What is the major advantage if you consider the two-port network? We can apply short-circuited and open-circuited condition. we can apply short circuited and open circuited conditions easily. By considering short circuited and open circuited conditions, we can extract that internally inside the transistor which one is a dependent parameter and which one is an independent parameter. Before going to design the amplifier, before analyzing all the parameters of the amplifier, first we have to know what are the dependent parameters and what are the independent parameters from the configuration. As we know that among CE, CB and CC, CE is the best configuration because voltage gain and as well as current gain is high or moderate compared with the CB and CC. In CB, voltage gain is maximum, current gain is equal to 1, approximately equal to 1, whereas in CC, voltage gain is approximately equal to 1, current gain is 0. From these three configurations, we are concluding that, for example, you consider for common base, voltage gain is maximum, but current gain is almost all minimum. Whereas in the common collector, voltage gain is minimum, current gain is maximum. Whereas if you observe for CE configuration, even compare with the CC configuration and CB configuration, voltage and current gains are not that much equivalent to CB and CC. Also, little bit high value of voltage gain and current gain we can experience from the common emitter configuration. That's why it can be used as a power amplifier. That is the extra application we can expect from the common emitter configuration. And that too, we are using in a major applications as a CE configuration. From this configuration, actually, if you want to work out the transistor as an amplifier, we know the biasing conditions. Biasing conditions are very crucial. So these are all the prerequisites already you are coming across in EDC. That's why I'm just trying to make the glimpse of what is the importance of this biasing and how it is equivalent to our parameters of the amplifier. Generally, in the biasing conditions, we require some external biasing with the combination of forward bias and reverse bias so that we can operate the transistor in the concerned area what we are expecting to our application. For example, if I want to use the transistor inside the amplifier, I require the input must be in forward bias and the output must be in reverse bias. And if I want to use the transistor as a open switch, nothing but we have to operate in cutoff region. The two open switch. And here an amplifier in the active region. If I want to use the transistor as an open switch, I have to operate in cutoff region. For that purpose, input must be in reverse bias and output is also in reverse bias. Of course, this is input side and this is output side, and this is input side and this is output side. For example, if I want to use the transistor in saturation region, I have to use it as closed switch. Then input must be in forward bias, output must be in forward bias. Both conditions, in both cases, input and output must be in forward bias only if I want to use the transistor in saturation region, that to closed switch. If I want to use the transistor as an inverter region, below cutoff region, I have to use the input as reverse bias and the output as forward bias. Exactly opposite to the active region condition that input is forward bias, output is reverse bias in amplifier case. Whereas in inverter region, the input is reverse bias and the output is forward bias. Here, all these regions we used to come across, especially in the configurations. This is the knowledge what we required from the configuration and at the same time the biasing conditions. Of course, we required some stabilization circuits and compensation circuits in order to continuously operate the transistor in particular the application what we are expecting, either an amplifier or closed switch or open switch. But here my idea and the discussion for this session is only I want to concentrate that on which region I want to operate if I want to use the transistor as an amplifier. So I am not concentrating on saturation, cutoff and inverter regions. My interest is only to concentrate. I want to use the transistor as an amplifier, that too in the active region only, so that I can operate the input as a forward bias as well as output as a reverse bias. This is my area of interest. In order to achieve this, input is forward bias and the output is reverse bias. For example, just now I am coming across that among 3 configurations, C is the best configuration. So that I am considering the transistor here. And I considered just now the transistor is an equivalent to a 2-port network. 2-port network is nothing but one is input port and other thing is output port, and one terminal is common. That is the meaning of 2-port network. So that is the basic condition of 2-port network. One terminal I am giving as an input, the another terminal is I am making as a ground, which is common between input and output. The other terminal is taking output. So here emitter is grounded and I am applying the input to the base. I am taking the output across the emitter. That's why I am making the equivalent to a 2-port network. Transistor is equivalent to a 2-port network. Here, the input, I want to find out the input current, so I require the ammeter here, connecting IV. If I want to find the input voltage between base and emitter, I require the voltmeter here. This is VBE. And it is a NPN transistor, as we know that. The NPN transistor is where input is forward bias, so that I am connecting forward bias, where P is connected positive terminal of the battery and N is connected to the negative terminal of the battery. It is a variable varying from 0 to 20 volts, and I am connecting across the input, that's why it is called VBB. And the current is moving from positive to negative, so I require the notations will be like this. Similarly, I want to check the output current, so I required one more ammeter at the output side. So I am connecting one more ammeter AC. As we know that the input side we are using forward bias and the output side we are using reverse bias. Collector terminal is a N type of terminal and it is connected to the positive terminal ports, and the remaining terminal is connected to the negative. This is positive and negative. I want to check the output voltage in between collector and emitter, so I required the one more voltmeter at the output side, that is known as VCE. Always current is going from positive to negative, so that this is the positive negative and positive negative. If you carefully observe this condition, the output is also variable, and I am applying VCC. I am applying the 2 sources here, one as the input side and one as the output side. These things already are coming across in configurations, but once again, why I am trying to stress, especially on this point, in the sense, from these configurations, we have to observe the input characteristics and output characteristics. Nothing but input is forward bias and the output is reverse bias. From that, we have to extract that which one is a dependent and which one is an independent. This is very crucial for us in order to understand the internal structure of, especially the transistor. Once you know the internal structure is equivalent to a 2-port network, then we can define that with respect to the electrical devices. Nothing but unless until you convert the transistor into electrical component and dependent voltage source and dependent current source, it is not possible to know that how this particular amplifier is depending upon internal. I have to design exclusively I have to design an amplifier for a certain applications depending upon the conditions. I have to know that what are the dependent and independent factors. That is the reason why we are concentrating on this configuration. So as we know that input is forward bias and the output is reverse bias. This is the NPN transistor what I am considering. Here I have to find out which one is dependent and which one is independent parameter. In this case, first I am observing the input characteristics. And here I am taking the output characteristics, especially. So if we carefully observe that input characteristics we used to observe in between the input current and input voltage. Input current is IB, input voltage is VBE, and the output current is IC, output voltage is VC. First, we will try to concentrate the input characteristics of a transistor by applying the forward bias. If you carefully observe that, I am observing the input characteristics in between emitter as well as base, where emitter is N-type terminal and base is P-type terminal. So indirectly, P-type terminal is base and emitter is N-type terminal. So here in the forward bias condition, emitter is negative terminal where it is connected to the negative terminal of the battery. Sorry. So emitter is a negative terminal where it is connected to the negative terminal of the battery. And the base is positive terminal where it have to connect the positive terminal of the battery. So indirectly it is a forward bias of a diode. As we know that the diode characteristics will explain us it is equivalent to a semiconductor. What is the meaning of semiconductor? Initially it will act as insulator. As you go on applying the supply, it is becoming as conductor. Those are the characteristics what we know that in lower standards. So that thing I want to highlight here. So initially there is no variation in current, and after that we can experience the variation of current like this. So the point where the current is increasing suddenly, as you go on increasing the supply, as the input supply VBB is go on increasing, then the input voltage is increasing, obviously current is increasing. So that the point where the current is increasing drastically, that point we are calling as cut-in voltage. This is very crucial. For a silicon, it will be 0.7. For germanium, it is 0.3. This is very crucial. For silicon, it is 0.7. For germanium, it is 0.3. These are the general diode characteristics what we are observing. But this characteristics is not sufficient for us to understand completely about the transistor. I have to see the condition that at what point of characteristics I am observing. At what point these characteristics are observed. So the condition is I have to observe the input characteristics of the transistor in the configurations by considering the VCE is constant. VCE is constant. That is the condition what I required. So by making first initially VCE as constant, and I have to come at the input side and I have to vary the input supply. According to that, I have to observe the input current and input voltage. So in this case, first initially I am considering VCE as constant. So based upon that, I used to observe three different characteristics. This is one case, and this is another case. By considering VCE as constant, let me give in detail about this. So by considering VCE as constant, first initially you consider VCE is equal to 0 volts for the first case. The second case you consider VCE is equal to 2 volts. In the third case you consider VCE is equal to 4 volts. As VCE is changing from 0 to 2, we have to observe that what will be the variation of IB current. As VCE is varying from 2 to 4, we have to observe that what will be the variation on IB current. So that is the case what we have to understand. Here, if you carefully observe that as VCE is varying from 0 to 2 volts, IB current is decreasing. Yeah, so let me explain in detail. So these are the three cases. I'm just making us like this. VCE as constant for these three cases. Now I'm drawing a line vertically here. In this case, I'm drawing a line vertically. And in this case, you can observe that at this point, at this point, and this point, and this point, as VCE is changing from 0 to 2 volts, from 2 to 4 volts, if you carefully observe here, IB current is decreasing. Nothing but the input current is depending upon the VCE. Input voltage is also varied, that we'll try to observe. Sorry, the input current is constant, but the VBE is trying to depending upon the VCE. Why? Because as emitter, base and collector, initially I am considering a condition that if it is a NPN transistor, I am applying the output as a reverse bias, input as forward bias. Input as forward bias. In this case, as the output reverse bias varying from 0 to 2 volts, this is the first case, 0 to 2 volts, we have to observe that what will be the variation on VB. Of course, IB is decreasing according to that. Why? Because the base width modulation, but IB is not depending upon the VCE. VB is depending upon the VCE. That we will try to see in detail about it. As VCE increases from 0 to 2 volts, what happens in the output junction means the potential energy barrier will increase. As the potential energy barrier increases, obviously IB current is decreasing, but we should not say that IB current is depending upon the VC. As the potential energy barrier increases at the output junction or the collector junction, obviously the base width will be decreases. This is a base width. Base width decreases. As base width is decreasing, the potential gradient across emitter and base will changes. Initially, the potential, if you carefully observe for this case, the potential gradient initially before having the base width, it will be having like this. Whereas, after making that base width is decreasing, the potential gradient will be decreasing like this. You try to understand that. Let me explain once again. As the reverse bias increases, potential energy barrier across the collector junction will increases. As potential energy barrier increases, base width will be decreasing. As base width will be decreasing, the sloping nature between emitter and base will changes. According to that, the cutting voltage what we are achieving will be affected. So that from this input characteristics, we concluded that VB is depending upon the VCE. VB is a dependent parameter, VCE is an independent parameter, and IB is also an independent parameter. So by observing this input characteristics, we should not conclude that IB is depending upon the VCE. IB obviously varies because of the base width will be changing. That is not depending. Why? Because the cutting voltage, whatever we are achieving after variation of the base width, the slopy nature of the in between emitter and base will changes. According to them, the cutting voltage will be affected. So from the input characteristics, we concluded, from the input characteristics, we are having three parameters. One is IB, another one is VBE, and another one is. So from the input characteristics, we are concluding that this is a dependent parameter. This dependent parameter. And these two are independent parameters. These two are independent parameters. This is dependent. So from this, we can conclude that VBE is a function of IB and nothing but input current and output voltage. So input current, according to the two-port network, we can consider it as, this is as V1, this is as F, I1, V2. From this, we can frame the equation that V1 is equal to H11 I1 plus H12 V2. We don't know about H11 and we don't know about H12. That we have to define once we calculate the output characteristics, and we have to identify that which one is dependent and which one is independent parameters. So this is V1. Of course, this is the thing what we are trying to analyze once you convert that particular transistor into a two-port network, and from the basic operation of forward bias and the reverse bias, we are concluding that which one is a dependent and which one is an independent parameter. And from the input characteristics, we concluded that input voltage VB is a dependent parameter and the input current IB and VC are independent parameters. Then we will come to the output characteristics of a transistor. Output characteristics of a transistor. We used to observe the output characteristics of a transistor in between the output current, that is nothing but IC, and output voltage. First, initially, these are the output characteristics are nothing but is in the reverse bias. Reverse bias characteristics are equivalent to a diode also, here also. Why? Because we used to observe the characteristics between base and collector apart from the emitter. And these are nothing but we used to apply the reverse bias. If it is a NPN transistor, this is reverse bias. Reverse bias characteristics, what we are achieving actually inside the diode will be like this. So we are trying to shift this quadrant to the positive quadrant, and reverse bias, both currents are in negative only. So according to our convenience, we are trying to shift this quadrant, fourth quadrant into second quadrant, third quadrant into second quadrant, and it will be like this. And finally, I want to fold it to the, everything is in the positive quadrant for our understanding purpose. We are getting the characteristics will be like this. So finally, the output characteristics of a transistor will be visualized like this. These are the output characteristics of a transistor. Especially these characteristics are nothing but a diode characteristics. Just now what I come across that just observing the characteristics is not sufficient, especially if you want to work out with the transistor. We have to identify that which one is a dependent, which one is a independent, at what condition we are observing this characteristic. Especially the characteristics, whatever we are observing, is by considering IB as a constant. By considering IB as, for example, I am taking as 50 microampere. So initially, I used to observe that I have considered the transistor by considering the input characteristics, and I am setting that input current is 50 microamperes. Why? Because just now what I am coming across the output characteristics. First, initially I am setting IB, and after that I used to observe the characteristics in between IC as well as VC. So that characteristics what I am getting will be like this. As if I vary the IB current from 50 to 100 microamperes, so that obviously the characteristics will be getting like this. IB is equal to 100 microamperes. Similarly, if I vary this IB is a little bit more from 100 microamperes to 200 microamperes or 150, then obviously I am getting the characteristics will be like this. Still, IB is equal to 200 microamperes. As IB current is varied from 50 microamperes to 100, from 100 microamperes to 200 microamperes, simultaneously we have to observe that at the 3 points where IC is also varied from IC1 to IC2, from IC2 to IC2. So this is the case what we have to observe. As IB is 0, IC is also 0. From the amplification factor of a transistor, we are working on a CE configuration that we know that beta is equal to IC by IB. This implies IC is equal to beta into IB, where IB increases, obviously IC also increases, IB decreases, obviously IC also decreases. So indirectly, the three parameters what I consider, that is IC, VCE and IB in the output characteristics, especially in the output characteristics. These are the three things what I consider. In this, we have to consider these two are independent parameters, and this is dependent parameter. It is dependent parameter. Okay. So from the output characteristics, we are concluding that IB is a depending upon the input current. Sorry, a little bit modification here. It is completely opposite I am coming across, where VCE and IB are independent parameter. The correction, whereas IC is dependent parameter. You please modify this. Output current is dependent. Input current and output voltage are independent parameters. This is the conclusion what I want to make from the output characteristics of a transistor. So from the input characteristics, we concluded that VBE is a function of IB, C. From the input characteristics, we are concluding that IC is a function of IB, and where finally from the configurations we are concluding that from the input characteristics VB is, these two are dependent parameters, and these two are independent parameters. So mathematically, dependent and independent parameters, we can frame it as VBE is equal to H. I don't know about that. I have to find out what is H. H11. Why? Because it is a two-port network. We are considering as IB. H12 we are considering as VCE. This is as equation 1. Similarly, IC is equal to H21 IB, H22 VCE. This is equation 2. Okay. These are the two things what we are framing from the input and output characteristics of the transistor. Based upon this equation, we have to model the internal behavior of a transistor. Without help of these equations, without knowing the knowledge of which one is a dependent and independent parameters, it's very difficult to find out or to define the internal structure of a transistor. If you carefully observe that everything is represented in the form of currents and voltages, and some cases we used to have the dependent, and another cases we used to have the independent voltage sources or dependent voltage sources and current sources. It is little bit easy for us to analyze. Why? Because we can easily apply short circuited and open circuited conditions, and we will try to extract all the what actually this H11 will explains, and H12 and H21 as well as H22, and how we have to relate these four parameters to the parameters of the amplifier. Okay, now from this we will try to frame. Once again, I am writing that equation, that VBE is equal to H11 IB, H12 VCE. This is with respect to the common emitter configuration, and with respect to the two-port network also we can consider V1 is equal to H11 I1 plus H12 V2, the second equation. IC is equal to H21 IB plus H22 VCE. With respect to the two-port network, I2 is equal to H21 I1 H22 V2. Now I have to find out what actually this H21 will explain and H222, sorry, okay, H22 and H11 as well as H1. In order to understand this condition, we used to apply the open circuited and short circuited condition. First, I am trying to frame these equations mathematically. V1 H11 I1 plus H12 V2. This is as equation 1. And I2 is equal to H21 I1 plus H22 V2. This is equation 2. So first, initially, I am applying the short circuited conditions. Short circuited condition at output of two-port network. So at the output side, I am applying the short circuited condition. As the output is short circuited, V2 is equal to 0. Substitute V2 is equal to 0 in equation 1 and equation 2. By substituting V2 is equal to 0 in equation 1 and 2, I am making that the resultant equation of 1 and 2 as V1 is equal to H11 I1 plus H12 V2 is equal to 0. Or directly I am considering V2. And this is making as 0. Then V1 is equal to H11 I1. This implies H11 is equal to V1 by V1. This is the case by considering V2 is equal to 0. The same V2 is equal to 0 I am substituting in the second equation. So in this equation also I have to substitute. For that case, I2 is equal to H21 I1 plus H22 V2. In this case, I am substituting V2 is equal to 0. This term is becoming, this is equal to 0. Here also it is equal to 0. And finally, I am getting as I2 is equal to H21 by I1. This implies H21 is equal to I2 by I1. This is the case by considering V2 is equal to 0. Similarly, if input is open circuited, this is a condition we used to apply on the above two equation of the two-port network. Why? Because I am considering the two-port network, and from that only I am framing this two equations, H parameter equations. Now I am applying the, if input is equal to open circuited, that is I1 is equal to 0, substitute I1 is equal to 0 in equation 1 and 2. After substituting I1 is equal to 0, I am getting that V1 is equal to H11 I1 plus H12 V2. This is the value is becoming 0, and finally I am getting as V1 by V2 is equal to H12 by considering I1 is equal to. Similarly, I2 is equal to H21 I1 plus H22 V2. Here also I am substituting I1 is equal to 0. Then you are getting as H22 is equal to I2 by V2. For the case of I1 is equal to 0. These are the remaining two equations what I am achieving from the second equation by making the condition as input as open circuit. So finally, I am extracting the values of H11, H21, H12, and H2. Okay. So from this, I am getting the, by applying the open circuited and short circuited conditions, finally I am extracting the four parameters known as H11, that is equal to, it is the, finally I am getting as V1 by I1 by considering V2 is equal to 0. Similarly, H21 I2 by I1 by considering V2 is equal to 0. H12, sorry, a little bit by V2 is equal to 0. H21, okay. H12 is equal to V1 by H12 is equal to V1 by V2. V1 by V2 by considering I1 is equal to 0. H22 is equal to I2 by V2 by considering I1 is equal to 0. If you carefully observe that the ratio of voltage and current will use us a value of a resistance. So this H11 will explains the resistance behavior, and I am observing that input port, that V1 is nothing but input voltage, I1 is nothing but input current. So I used to observe the ratio of input voltage with respect to input current, so that I am considering as H11 as input resistance. So that I am making as HI. HI is nothing but H parameter which explains the behavior of a resistance, and that too I am representing the suffix I as input side. And now I am using these parameters of a common emitter configuration equation, or the common emitter configuration forward bias and reverse bias, so that I am considering as HIE. Similarly, H21, if you carefully observe that the ratio of output current by input current, H21 will explains that ratio of output current by input current. So that the ratio of output current by input current is nothing but gain. Output current by input current is nothing but gain. And I am observing that it is a current gain, and that too forward current gain. Output by input is forward, input by output is reverse. So that I am observing the forward current gain, so that I can consider it as forward HF, of course current gain, and I am observing these parameters on the common emitter configuration, so it is defined as HFV. Similarly, the another parameter known as H12. So this will explains that input voltage by output voltage, that is also gain, but I am taking the voltage as the important parameter here. At the input side as a voltage, and the output side is also a voltage only. That's why it is called the voltage gain. Actually, if I take the numerator as a output and the denominator as an input, then is an actual calculation of a gain. But it is reverse. That's why it is called the reverse voltage gain. Reverse voltage gain. It is defined as HR, and that too we are using the common emitter configuration, so it is defined as HRE. Similarly, from the output characteristics, one more parameter we are defining, that is H22. It is also representing some type of a resistance, so that, but it is having the inverse ratio of current as well as voltage. That's why it is called as admittance. And that too I am considering the output current with respect to the output voltage, so that I am considering as output admittance. Is also one more parameter which are related to the output characteristics. H, output admittance, in the suffix I am representing O, that is nothing but output side I am considering this parameter, and that too common emitter configuration, and finally I am considering as E. If I represent the same parameters with respect to the common base, I used to have the HIB, HFB, HRB, and HOB. If I am represent with respect to the common collector, I can represent HIC, HFC, HRC, HOC. This is with respect to common collector. This is with respect to common base, and these are the parameters with respect to common. So finally, from the configuration of a transistor, I am trying to frame the internal structure of the transistor with respect to the H parameter. Now everything you will try to frame it with respect to the equations. And from that equations, we will try to make the AC equivalent model or hybrid equivalent model of a transistor. So what is the necessary of spending more time all these parameters means I have to define the internal model of a transistor. For that purpose only I am concentrating here. So that I am once again framing the final equation with respect to the common emitter configuration. I want to concentrate common emitter configuration. So that the input parameter which is defined as VBE, VBE is a dependent. Similarly, IC is also dependent. And from that I used to frame that HIE IB plus HRE VCE HFE IB IB and HOE VCE. Here I want to make a clarity that I have to find out the variation of current and the variation of voltages with respect to this variation of VB and IC. So that everything I have to represent in the dynamic values. In dynamic values, I used to observe what will be the variation of VBE, what is the variation with respect to the variation of IB, what will be the variation of VBE with respect to the variation of VC. Similarly, the variations of output current with the variations of input current as well as output voltage. So for that purpose, I have to represent in the form of dynamic values, so that everything we am representing with respect to dynamic values. HIE IB plus HRE VCE. Similarly, IC is equal to HFV IB plus HOE VC. So this is a final H parameter model for a transistor. AC equivalent model or hybrid model of a transistor. Okay, so unless until if you are not defining this AC equivalent model, it is not possible for us to know the internal structure of the transistor. From this equations, we will try to construct or we will try to draw the AC equivalent model, and from that we will try to evaluate all the parameters which are related with the amplifier. Once if you know the model, then we can easily find out all the parameters of the amplifier like voltage gain, current gain, input resistance as well as output resistance. Once you know all these four parameters, then we can easily design any amplifier for any condition, for any type of applications as well as any type of frequencies. That is our aim. So in order to find all the parameters of the amplifier, first we have to know that what will be the internal structure of the transistor. That internal structure I am framing from the H parameters. Unless until you, if you're not considering the transistor is equivalent to a two-port network, it is not possible to find out all these parameters. Why? Because it is not possible to apply any open circuited and short circuited conditions unless until if you are not considering transistor is a two-port network. Anyway, finally, we are coming at the end of the main working principles, whatever we are coming across in the two-port network of a transistor. And finally, we are framing the AC equivalent model. So with respect to that, I am drawing a AC equivalent model or hybrid model of a transistor in CE configuration, especially in CE configuration. Hybrid model of a transistor in CE configuration. As we know that, once again I am trying to write down that equation. VBE is equal to HIE into IB plus HRE into VCE. Similarly, IC is equal to HFE into IB plus HOE into VC. So this is equation 1, this is equation 2. If you carefully observe that the voltage, what I am considering. First, initially, I am framing the first two parameters of the first equation. One is HIE and the other one is HRE. HIE will define the resistive behavior. And HRE, if you carefully observe here, HRE is nothing but, by considering input as open circuited, as we know that VBE by VCE, so that VBE is equal to HRE into VCE. So that indirectly HRE VCE is explaining the voltage behavior, so that I am considering as a dependent voltage source, that is, which is equivalent to VBE, this is IB, and this is HIE, and this is HRE VCE. I am trying to frame the equation 1 in this form, in the form of parametric representation, in the form of a model. You carefully observe that applying the KVL here, VBE, HIE, IB plus HRE into VC. It is a dependent voltage source, which is a dependent voltage source. This is dependent voltage source. And here the input resistant behavior, HIE will explain the resistant behavior. And if you carefully observe that the resistance is series with the voltage source, which is equivalent to a Thevenin's equivalent. The first equation is representing which is equivalent to a Thevenin's equivalent. How many voltage sources having inside the transistor, everything is combining as a single voltage source, and how many resistance behavior are there, everything is considering as a single resistance. By connecting the resistance series with the voltage source, that equivalent we are considering as a Thevenin equivalent circuit. On the input side, we can experience the Thevenin equivalent circuit, and from the equation 1, we are trying to frame the model in the form of a resistance as well as dependent voltage source. And similarly, from equation 2, we have to consider that IC is trying to distribute in the form of a current gain. And for example, you consider IC is equal to HFE into IB, nothing but the collector current is represented with respect to HFE and IB. That current behavior I am representing with respect to the current source, dependent current source, known as HFE IB. This is a dependent current source. And similarly, from the second part of the second equation, I am considering IC by VCE is equal to HOE. This nature is nothing but opposite to a resistance, nothing but admittance. Even the admittance also is representing with respect to the resistance. So I am representing HOE behavior with respect to the resistance, that is HOE, so that I am considering this is IC and this is VC. This is grounded, and the input I am applying across the base, the output is taken across the collector, and which is emitter is common. Now, if you carefully observe here, the output side is nothing but one dependent current source and one resistance which is connected in parallel. And this thing I am considering which is equivalent to a Norton's equivalent circuit, where how many current sources are there, everything we used to combine as a single current source, and whatever the resistors are there, everything we used to combine the single resistance which are connected parallel with that current source, that is becoming as Norton's equivalent. Anyway, indirectly I am trying to frame the model with respect to the dependent voltage source and dependent current source with respect to the linear elements. Unless until if you are not considering the internal behavior of a transistor as a linear element, it is not possible to find out that what are the parameters which are influencing on the parameters of the amp. Then only we can easily design, then only we can easily control, then only we can easily modify internal structure of that amplifier. Once you consider the internal structure of this particular transistor is equivalent to a linear element. Generally, transistor is a non-linear device, but By considering the transistor is equivalent to a two-port network, we are trying to convert everything in the form of linear elements internal behavior of a transistor. Then it is one of the important step what we are considering. Once you define everything is in the form of linear elements, it is more convenient for us. Already from the electrostatics and as well as from the circuit theory, it is more convenient for us once you convert it to equivalent model. So with this, I want to conclude that. Thank you.